Hi there, I'm Aria Beingessner. You might better know me as Gankra from my time working on Rust back in like 2015 when I was on the Libs team, and I did things like the Rustonomicon and learned Rust with entirely too many linked lists. But these days, I don't really do much contribution to Rust itself. I mostly work on Firefox, and particularly the dev tooling, like our crash reporter or our build systems. But a few months ago, I got really frustrated about an old thing that bothered me back when I was working on the Rustonomicon. And what came out of that was something called Strict Provenance. And it's a set of new APIs in the standard library that you can use today. And the core idea behind Strict Provenance is just, what if we pretended unsafe code was nice? And then it was, because we pretended. It's a very strange idea, and it's weird because the idea is very strange, but the APIs are very simple. They're like a few lines of code, you can write them on stable Rust. They really don't do anything terribly special, but it's the ideas behind them. And for that, you're going to need some background. And, well, I'm afraid to tell you, I've lied to you, and I've locked the doors. There's no escaping. I'm going to try to explain memory models. And you're going to have to sit through it. So, why do we have this thing called a memory model? And fundamentally, it's about the fact that programs need memory to represent their state, but that using memory is in some sense bad. We don't want to be accessing memory because it's slow, and if we use too much memory, our program will crash because it's finite. But at the same time, we also don't want to write super ridiculously low-level and platform-specific programs that, say, explicitly refer to the registers on ARM or the registers on x86. So we want to write programs in a kind of high-level way that uses memory, and then give the compiler the latitude to reason about that memory more abstractly and in a first-class way. And so something like a local variable or a global variable or a call to malloc is an abstract allocation that the compiler can optimize around and can remove accesses to, or even remove the allocation altogether. Yes, the compiler can in fact see a malloc and free pair and say, you're not using that you're not using that enough to justify it, and just remove it. That surprises a lot of people when they first learn that. It surprised me. And okay, so we can write our programs in a very high-level way, and the compiler will clean it up for us. And if that was the whole story, then everything would be great, right? But the problem is, programmers love to do cute memory tricks, and then compilers make the programmers go away. Because they did something the compiler didn't think could happen, and it miscompiled or misoptimized their code, at least as far as the programmer is concerned. The compiler might disagree. The compiler thinks it's perfect. Compilers do have bugs, though. Pro tip. It happens. You're probably not running into a compiler bug, but they happen. More than I'd like. So to explain that, to explain memory models to you, we're going to look at Puzzle Club. Now, you love puzzles. Who doesn't love puzzles? And so you're going to make a puzzle solving club, because that's the best way to solve puzzles. But of course, everyone knows a club needs a treehouse. All right, let me explain what on earth I'm talking about. In this metaphor, people are pointers and puzzles are state. So we want to work with state in some way, and we need pointers to do that. And so we're going to create an allocation to contain our state. And allocations need memories. Our treehouse is memory. And our club is an allocation. And this, normally we would say, oh, the club is the treehouse, but by separating these notions, it lets us eliminate the treehouse or not access the treehouse if we don't really need to. The club was inside us all along. So let's look at Puzzle Club's founder. What do we know about them? They love puzzles, and they're a metaphor for pointers. Okay, so pointy puzzle lover. Oh, that's Pinhead. Okay, now let's look at Pinhead's terrible treehouse. Well, I mean, it's a pretty bad treehouse, but it could be worse. It could be taller, because memory is slow. It takes us a while to climb up and down this treehouse. But no, it could still be worse. It's also on terrible clip art fire. And what that means is we can't really be in this treehouse for long. We can climb up it, we can grab some stuff in it, we can put some stuff in it, but we need to get it out of there fast. And what I'm really saying here is most things can't be done in memory. We need to take our memory and load it up into registers like the really low-level state of a CPU and manipulate it there. And I'm going to be summarizing that concept as just calling it caching. There can be caching in various forms, and generally we want to be caching things. But it is worth noting that this caching is in a lot of cases like a matter of correctness. Like there are certain operations you simply cannot do in memory. So it's important that compilers know that they can put things in registers because they have to put things in registers. Okay, so now let's look at Pinhead's really naive source code for solving puzzles. They're going to climb up, they're going to grab two pieces, climb back down, check if they match, and then climb right back up, put those two pieces back, grab another two pieces, and do that over and over and over and over. Hopefully you can see this is miserable and bad, and Pinhead's going to catch on fire eventually. This is going to take forever, and we don't want this program. We want the compiler to clean this up. So let's look at the easiest case for the compiler cleanup. It's just Pinhead in Puzzle Club. It's just one pointer manipulating this one allocation. Well, in that case, why even keep the puzzle up in the treehouse? Let's just go home and go to bed. Work on it in our bed and at our own leisure, at our own comfort, as fast as we can. And then I guess if we still care about the treehouse, we could put it back at the end. But actually just screw the treehouse. Let's just not even build the treehouse. Let's skip this allocation altogether. Why did we say clubs need treehouses? I don't know. That's what I was told. Okay, but this works fine for simple, small puzzles that are easy to solve. Let's look at some harder puzzles. Now we're going to need a friend to help us with the puzzle. So we're going to really need to use the club. But they are our friend. In fact, they're our best friend. They live in the same house as us, which is to say they're in the same function. And as it turns out, this really isn't a problem. You two are so in sync. You see exactly what you're doing. There's still no problems. You can work on the puzzle together. You're not going to randomly slap the puzzle out of the other person's hand. You're just going to work perfectly in sync. And so we can still have this logical allocation with multiple pointers into it. And we still don't need the memory backing it. Or we can avoid accessing the memory as much as possible if, for whatever reason, we decide the treehouse is important. But now our puzzles are going to get even harder. And so we're going to have to bring in a ringer, by which I mean a subroutine. And now we don't have this same amount of perfect information in sync. So we're going to have to genuinely take some turns working on this puzzle. And so now the treehouse really is fundamentally important because we need somewhere to synchronize the puzzle state while we're going back and forth. And I might say some words that sound like I'm talking about atomics, but everything we're talking about is single-threaded. Don't worry about atomics. Even in single-threaded code, you do need to synchronize state when you have caching. because two different parts of your program might not know about each other and need to agree on the state. But we can still do some caching while we're taking turns. We just have to be sure to, at the start of our turn, climb up, grab the puzzle, don't make any assumptions about how it was before. Now, at that point, we can do some caching. We can work on it in the grass at the bottom of the tree. And then, when we see the other person walking up to the tree, when we see the other pointer going to access that memory, we have to write back all of our state, so that when that pointer climbs up and reads it, they don't see that like half the puzzle is missing and freak out and do something terrible. Because, you know, God forbid you work on a puzzle and there's a missing piece, you might as well burn down your already burning down Treehouse. Okay, so now that we've looked at some of the simple cases and how the more local and precise information we have about something, the more we can eliminate uses of memory, I'm sure you're wondering about the thing that immediately jumps to mind when you think about memory models, and that's wandering plumbers. Classic computer science problem. There's this wandering plumber who thinks there's a bathroom around here, sees your treehouse, climbs up it, and, like, I don't know, sees your puzzle pieces and, like, caulks them to the floor because it thinks they're bathroom tiles? That sucks. What? Oh, it's memory corruption. We're talking about memory corruption here. If there's some other unrelated pointers that think your memory is something else, they're going to make a mess of it. If there's a plumber who walks into your puzzle club and thinks your puzzle is bathroom tiles, they're going to make a mess of it. We don't want this. So, we need security. But the question is, how do we get security? Well, we're going to get a guard for our club, and we're going to say this guard will only let members in. But this is still kind of kicking the can down the road because, well, who's a member? And kind of circularly, a member is whoever we invite. Just a member is anyone another member has invited. So when the club is founded, there's a single founding member who built the treehouse, and they invite other people who are then allowed in. But okay, I've been lying to you a bit here. Sorry. This is provenance. This idea of membership is just defined by other members inviting other members. This chaining of membership from people, this is provenance. It's just pointers get access to memory because other pointers said they could. But, okay, here's that lie I was starting to get to. Pinhead doesn't have any friends. Pinhead only has clones. That's why all these friends have looked exactly like him. Yeah. When you're writing a program, you don't ever do this like operation where you're like, oh, hey, other pointer, you're a member of my club now. No, you never do that. What you do in a program is you copy pointers or you offset pointers. And all those copies and offsets, those are basically clones of the one true original pointer that founded the allocation, like the return value of malloc or the variable name of a local variable. And all of those are implicitly members of the club. And actually, in the reverse, they're only members of that club. They're not allowed to join any other club because they're your clones. They're here to solve puzzles for you. They don't get to go to hairdressing club. They have to be in puzzle club. So let's get philosophical. Is this guard actually real? We've said we need security and that we need this guard dog protecting our clubhouse. But do we really need it? Because, like, if everyone agreed that you're not supposed to wander into other people's clubhouses, and everyone assumes everyone else sets up a guard dog to protect their clubhouses, well, you're not going to go wandering up into random clubhouses anymore, are you? You're just going to assume there's a guard dog and stay away. You're only going to stick to your clubhouse. And so, if everyone's already acting as if there is a guard dog, do we need a guard dog? Would anyone notice if our guard dog fell asleep? Probably not. And so this philosophical distinction is one that actually shows up in different implementations of this approach. Because everyone agrees that conceptually there is a guard dog, but they don't agree on whether it needs to exist. And so from that, you get dynamic checkers, which actually do install the guard dog and make sure that everyone stays in their clubhouse. And on the other side, we have static optimizers like Rust-C, like our compilers, which just assume there's a guard dog and use that to make the code go faster, or to make the code correct at all. Because remember, caching is sometimes semantically important. So, on the side of definitely we need guard dogs, well, crimes are real, we want to catch bugs, and we want to secure our system. We have our dynamic checkers. These are things you might not be as familiar with working on Rust code. There's kind of two important cases that I want to talk about in this talk. There's Miri, the Rust interpreter, which basically runs your program in like a fully sandboxed environment and keeps track of everything perfectly, and will catch things like someone in Puzzle Club trying to access Hairdressing Club, or vice versa, or Wandering Plumbers, or whatever. And we have this thing called Cherry, which is take this concept to the hardware. And the most notable implementation of Cherry right now is Morello, which is built on top of ARM. It's physical hardware that actually exists. And it will actually enforce these. It will actually, at runtime, check these guards and and crash your program if a pointer gets out of its club, if it accesses another allocation. Now, on the flip side, we have static compilers. And their entire thesis statement is just, well, you can't commit crimes because that's illegal. How would you do it? It's illegal. And guards are expensive. And I want to go fast. Or at least my users want my code to go fast. And this is the philosophy of Rust-C, Swift-C, Clang, GCC, all your static compilers. They all are built on this premise of people follow the rules. And especially for low-level things like memory models. Now, remember, in both models, we are still assuming the guards exist. And regardless of whether we want to do checking or optimizations, we do need to be tracking clones. The dynamic checkers want to be tracking them to make sure that things are correct and to catch bugs. And the static optimizers want to track them just so they can say, oh, you don't actually need to climb the tree this time because no one's around who would notice. So, we need to deal with clone containment and tracking. And what happens when clones escape? And what happens when mysterious strangers show up that we don't know about? And our answers to this and our approaches to this depend on how we do our tracking. And our different approaches, static versus runtime and Miri versus Cherry, kind of changes how this clone biohazard containment process works. So we're going to go through them. So first off, we have static tracking. Compilers like to really function locally. They want to be zoomed in on a single function and do all the reasoning there, and then do that for all the functions individually and then put the parts together. Because they're so zoomed in on just one thing, it's really easy to escape their view. If you call a function and pass another pointer into it, that pointer has escaped into that function. But we can see it happen. And we call those situations where it happens, or rather, we can see these situations where a pointer escapes our view and call those exposing. We call that exposing. And it's important to keep in mind that this is kind of a conservative statement, because when you pass a pointer into a function, the kind of things we're worried about is, oh, you stored that pointer in another allocation, or you put in like a global variable or something, and now something that I didn't think was a clone could be a clone, and everything goes wrong. So all these exposing operations are like operations where you could do something bad, and I'm forced to assume that you did do something bad because I want to be correct no matter what happened. And so we're going to assume this worst case scenario, and we're going to mark, and when one of our clones escapes our view and exposes our allocation, we're going to mark that allocation as a biohazard. And we'll look at what that means in a moment. On the flip side, we have when pointers come from outside of our view and we have no idea where they came from. Is this stranger one of our clones, or is it a member of another club? Thankfully, again, we can see when they happen. So we can mark when they happen. And again, mark them as biohazards. So the significance of this is once this stranger wanders into the woods, and I'm down in the grass working on my puzzle underneath my clubhouse, and I see a stranger walking in the woods. I see a pointer is about to access some memory. I need to know if that stranger is going to wander up into my clubhouse. If they are, I need to scramble up that tree, put the puzzle back so that they can work with it. If they're not, I can stay in the grass and keep doing stuff. I can keep things cached. So the idea with the biohazards, with this exposing, is to put everything that is a biohazard into one mega club. We just say all biohazards, assume all biohazards are in one allocation and they're all clones of each other. And so any two biohazard accesses have to be pretty naively compiled. They all need to take turns. And so in the limit, we end up with this, like the original really naive code gen that we really didn't want. But critically, if I'm working on my puzzle under my treehouse, and my treehouse isn't marked as a biohazard because it hasn't been exposed, that means so far I've perfectly tracked my allocation. And so, if I see a biohazard clone walking by, I don't need to worry about it. So I can still get all of the good, fast, cached code gen that we want for the parts that we do track perfectly, and then the really conservative code gen for the parts we don't. So we get kind of a graceful degradation of our code gen. That's really important and good. Now, on to runtime tracking. Miri, unlike our function, our compiler, which is zoomed in on a function, Miri is looking at the whole program and dynamically. And that means it basically sees the whole world, right? So nothing can ever possibly escape its view. And furthermore, Miri makes all of the pointers hold ID cards, and it will check those ID cards whenever you access the memory. Those ID cards are kind of like keys into a hash table. They contain a bunch of different metadata that Miri checks. I'm not going to try and enumerate it all, but there's a bunch of different things that it will check. But actually, does it have a view of the whole world? Because there's places with dragons. There's places with native code. So really, Miri's not really having a view of the whole world. It has a view of Rust. It more has a view of like a country. And inside that country, it knows everything that's going on. It knows all about the Rust code. And it can check every access in Rust code. But anytime we call into some C code or like a system API or do any kind of FFI, any call into another language or another program or library, Miri can't track it anymore. And that's a problem because Miri is ultimately not compatible with native code. It can shim some known APIs. So like if you call file open, it'll know what to do to like shim that. If you call certain Linux APIs, it knows what to do to basically emulate those Linux APIs. But in the general case, it'll just crash. It'll just be like, I don't know what to do here, crash the program. And that's a frustrating thing for people who are trying to like use Miri to catch all their bugs. If they do a lot of system APIs, Miri might not know about them yet. It's a very manual process to deal with this. But Cherry has truly conquered its world. It is the hardware. Everything that runs on the system is running under Cherry. It has become native code. There is no incompatibility with native code. You need to be compatible with it. And so it truly does have perfect tracking. Except for time travelers. It can't track time travelers. And the reason it can't track time travelers is because Cherry is actually implemented in a very specific way to kind of balance performance and precision. What a Cherry pointer is, well, for one, it's twice as big. So for a 64-bit system, it's actually 128-bit pointers. And what they store in those extra bits is an entire other slice, like a Rust slice saying, like, here's the range of memory that this pointer is allowed to search around in. And that is that membership ID that we were talking about. It's saying, like, hey, Puzzle Club is this big, this pointer is allowed to wander around in this area. And if it breaks out, you get a fault and the program crashes. But that doesn't work with Theseus's Puzzle Club. So, consider, we've solved a bunch of puzzles, everyone's retired as champions from all puzzles forever, and now no one's left in the club. So let's just cut down the tree, let's free that allocation. But, you know, time will pass, eventually that tree will regrow, and also catch on fire for some reason, and someone will build another clubhouse in there, and it'll be Hairdresser Club or whatever. Is this the same club? Or is it not? Can our old clones enter this clubhouse? Can Puzzle Club clones enter this clubhouse? It's where their club was, there's a club there. As far as Cherry is concerned, with its, oh, I track where pointers can be, this is fine. Because, oh, a pointer is just a location. But no, it's not. That's a use after free. We don't like this. This clone has become a freelance plumber in its retirement. That's no good. We can't let this puzzle-solving plumber wander into Hairdresser Club. And so clearly, just thinking of the like membership tracking of this guard as just a location is insufficient. We need to add what people call a temporal component, but really what they're saying is just you need to know what club you were actually part of at this location. Your membership says what location you lived at and what the club was. And we call that temporal because it only really matters when time passes, because it only matters when clubs can go away and then something new can show up in that place. But really it's just remembering the club we were in. And I don't really have time to get into this, but it is interesting that this actually is kind of a fractal thing because we care about allocators in some sense, but your system, your program, has a lot of nested allocators because there's like the kernel allocator, and then malloc allocates pages from that, and your program allocates slices of memory from malloc, and then you subslice that memory with like borrows and stuff, and like there's something interesting here, and that becomes stacked borrows if you ever heard that, but we're not going to get into stacked borrows. What we are going to talk about is transcending reality. So, your clones have learned how to become pure energy. And by that I mean, they have learned how to become integers. Now, this raises some more philosophical questions. Because when they become flesh, when they finish going on their trans-existential journey and stop being a hive mind with all the other energy, are they still a member of our club? How would we know that? Did their membership ID turn into energy with them and follow them? Or did they drop it on the ground? And as it turns out, both of those are valid answers. So let's look at how our different approaches kind of try to address this question. Our static compilers say, actually, this is kind of okay. They mostly want to reason spatially. So regardless of your answer, if you just end up with, if you drop your membership on the ground, I don't really care. And if you, and the static compilers already have these biohazard protocols, these exposing protocols. And so what they can do is say, well, if you have a pointer to a club and you turn it into an integer, we'll just mark that club as a biohazard, or mark that allocation as a biohazard. And when you turn an integer back into a pointer, we're going to treat that as exposed. We're going to treat that as a biohazard. And basically what this means is we're going to be really conservative whenever you do these operations. And that's basically all you really need to do to be careful about this transcendence stuff, is just be careful when these operations happen. And unfortunately, our compiler backends don't really do this. And this is one of the frustrations I had that got me to work on this stuff. We'll get into, well, the high-level detail is just LLVM doesn't want to treat turning a pointer into an integer as an exposing operation, because that would pessimize all the code that touches that allocation. But you need to do it because otherwise you can get miscompilations, and they do exist. But the real trouble is when you start getting into the dynamic stuff. Dynamic transcendence is really, truly problematic. Because now we really do need to answer that question about what happens when it turns into energy. Does it drop its membership on the ground, or does it take it with it? Because in something like Cherry, a pointer is 128 bits wide, but the address part, that's only 64 bits wide. So if I could just get the address part, that's a big space savings. That'll cut my memory usage in half. And really, most of the time, people are actually only interested in the address part. But maybe they want to do this, they want to come back as a pointer, and maybe that means I need to carry all the bits around. And yeah, the address part, the version where you just turn into an address really is problematic, because for the dynamic checkers, it's kind of impossible to answer the question, what membership does it get? Because you threw out these bits that were part of the pointer. One solution is to allow forging of membership IDs. We saw with the static compiler that allowing these things, or tracking this concept of exposing, kind of made everything okay. So what if we dynamically model that concept? And basically, when we turn an integer back into a pointer, we look at all of the currently exposed allocations and check if it's inside of one. We do a hit test on them. And if it is inside of one, well, we just forge an ID for it. Now, this leads to two problems. The philosophical problem that frustrates me, which might not be that big of a problem in practice, but still annoying, is this basically reintroduces the concept of a use after free, as long as you do it through transcendence, through integer casts. And because remember, use after frees were a problem when we wanted our memberships to just be a location. We needed to add this temporal component, this what club you were actually part of component. And this notion of just doing like a hit test is basically saying, well, really only the spatial component, only the address really matters. And so that means you can get use after freeze again, and your checker just has to say, I guess you know what you're doing. And I don't like that. The more serious problem is for Cherry. Those bits are important and they can't be forged. Like Cherry doesn't, the way Cherry works, it can't like reconstitute that slice that was stored inside the pointer. That's gone. It doesn't know what to put there. So this just doesn't work. And so Cherry needed to find a solution. And they came up with a very simple solution, which was just, hey, find a sponsor. When you turn yourself from pure energy from an integer back into a pointer, just find someone who's in your club and get them to vouch for you. And when they do vouch for you, just copy their membership, copy those bits. And the reason this is better is because it kind of fundamentally proves that you knew where you were supposed to be. Because not only did you know the location that you were supposed to be, but you knew someone else who is in that club, who has access to that allocation, which generally would not be the case if you were doing an actual use after free. And that simple idea of finding sponsorship, that's what strict provenance is. That's the whole idea with these APIs. So the pretending if everything was nicer is just pretend that we have to do this operation, that we have to do this sponsorship operation, because it cleans up this weird, nasty edge case of going from a pointer to an integer to a pointer and losing information. It kind of cleans up the last little hole in tracking pointers. But all your old stuff still works the same. It's just using these APIs makes the new stuff more precise, and if you're compiling for something like Cherry or something like Miri, they'll work better, or at all in the case of Cherry. So we're already way over time, but we're going to look at some of the APIs. With adder is this new with adder operation that we've added to pointers is the sponsorship operation. So rather than saying some address as *const, we'll just say, hey, sponsor pointer, make a copy of yourself with this new address. So we're turning this unary cast, this one operation cast, to a binary cast. That's the main thing with strict provenance, just this one API. Everything else is things to be more explicit or convenience APIs. In the case of being more explicit, we now have APIs to be explicit about whether you actually meant to expose or not. Because remember, LLVM doesn't want to make integer cast pointer to integer be exposing because it'll pessimize things. So let's just make that explicit so that we can say whether we really did need the exposing or we didn't. So if you're just doing something like, hey, I want to cast a pointer to an integer because I want to check if it's aligned, you're not going to turn that integer back into the pointer, so you don't need to expose the address. You're not going to let the clones escape, basically. And so you have these two options. And the second one, .adder, is shorter because that's the one you usually want. And because that's what LLVM is assuming today anyway. So even though it's like technically more dangerous because it's saying like, assume I'm not going to let this escape and do bad stuff, that's just what the compiler's already assuming. And then we have some API, in a similar vein, we kind of have these APIs for doing an integer to a pointer as a unary operation, but more explicit about which thing you're trying to use. Are you actually just creating an invalid pointer, like say pointer dangling for those who know about it? Or are you actually relying on exposure as an operation? And when you do that, we can either say like, oh, your code won't work on Cherry, or we can try and work out what to do. This gives us more flexibility as how to handle all these other platforms or these dynamic checkers. And not strictly part of strict provenance, but kind of a fallout of it, is we added a bunch of convenience APIs. So now you can check, is this pointer aligned? or is this pointer aligned to this given alignment? Or you can say, hey, offset this pointer by some byte amount. So instead of like by the stride, just be like, I want this pointer to increase by 3 bytes. And we even added some more operations to atomic pointers so that you can stay in pointers. That's kind of one of the big takeaways is treat things that are pointers as pointers, or things that might be pointers as pointers. One of the mantras I had to repeat a lot was just, if something is like a pointer or an integer, treat that as a pointer. Because in the past, a lot of people have said, oh, I'll treat that as an integer, because that's more convenient. That's also saying the compiler, it's basically an integer, don't worry about tracking it. Compilers track pointers a lot more carefully, and we want to stay in that mode so that they track more carefully. We want to tell them to track the clones rather than this pure energy floating through the ether. And just as a final detail, all of this, even though these are all unstable APIs on in the core library or the standard library right now, most of them are available in the strict provenance polyfill S pointer. Because, as I've said, a lot of this code is really trivial. It's like a few lines of code. It's like just do a pointer offset. But yeah, so that's Puzzle Club. Hopefully now you perfectly understand memory models and could write a PhD thesis on it. I'm sure you can. Puzzle Club is such an elegant and simple concept. It's perfect. I don't know. This talk's done. Have a good lunch. Peace.